Right, let's continue to question number 21, page 719. A resistor of 900 ohm, a capacitor of 0.25 microfarad, and inductor L 2.5 Henry are connected in series across 2.4 times 10 to the power of 2 Hertz AC source, for which the delta V max is this amount. Calculate the impedance of the circuit. Okay, so we want to calculate the impedance of the circuit. Alright, so for part A, alright, the impedance, okay, we need to determine the Z equivalent to square root of R square plus XL minus XC square of this, square root everything. Okay, but then we have to calculate the XL and XC first. XL is equivalent to 2 pi FL, which give you 2 pi times 240 times with 2.5 Henry, give you 3.77 times 10 to the power of 3 ohm. For XC, okay, is 1 over 2 pi FC, equivalent to 1 over 2 pi. F is 240. Your C is 0.25 micro 10 to the power of negative 6 farad, which give you 2.65 times 10 to the power of 3 ohm. Right, therefore finally your Z is equivalent to square root of 900, your resistor, square, plus XL 3.77 times 10 to the power of 3 minus 2.65 times 10 to the power of 3. Then square everything. You will get your answer as 1.44 kilo ohm. Right, that is for A. For part B, right, for part B, the maximum current delivered by the source, okay, the maximum current, so I max equivalent to delta V max over the impedance Z, right, which give you 140 volt as given here, okay, divided by our answer just now, 1.44 kilo ohm, right, which equivalent to 0.0972 ampere. Okay, then part C, for part C, right, the phase angle between the current and the voltage. See, phase angle phi equivalent to arctangent of, right, XL minus XC over R, which give you 51.2 degree. And then part D is the current leading or lagging the voltage. This is very important question. So for part D, okay, you need to check your phi. Your phi is positive, it's bigger than 0, it's positive, or in other words, it's positive, right? Therefore, okay, voltage, the delta V, leads the current. Okay, so this is the exercise. Next one is about power. Okay, no power loss are associated with pure capacitors and pure inductors in an AC circuit. Why is it? Okay, because in a pure capacitor, during one half of the circle, energy is stored, and during the other half, the negative part there, the energy is returned to the circuit. Alright, so if we refer to the sinusoidal wave function, right, it's like this. It's about current, right? I versus T. So what does that mean by of this? In a pure capacitor, during one half of the cycle, energy is stored. During the other half, energy is returned to the circuit. So it means that this is the first half, energy is stored. When the current reverse the direction, because we are talking about AC, right, alternating, when the current is reversed in direction, so the energy stored within the capacitor will be released to the circuit. That is why no power loss, okay, in the capacitor. Alright. No power loss as well. Okay, no power loss as well. No power loss as well. Okay, in the inductor. Okay, because in pure inductor, okay, the source does work against the back EMF of the inductor. Okay, and energy is stored in the inductor. But when the current begins to decrease, okay, the energy is returned to the circuit. So goes the same. At the first half, okay, the inductor going to produce its own opposition, or we call it back EMF. Okay, so the induced EMF, induced current, induced voltage there, induced B there, going to oppose the changes. Then whenever the current from the power source is reversed in direction, the inductor going to release the energy built up within the solenoid or inductor just now to the circuit. That is why the power loss in the inductor, a pure inductor, must be pure inductor, also zero. Okay, then power in AC circuit only coming from actually the resistor. Okay, the resistor is the one that causing the circuit to lose the energy in terms of heat. Okay, so average power, okay, is equivalent to power average is equivalent to IV, okay, which is within the resistor. So if I rewrite this one, okay, power average is actually I flowing within the circuit times with the delta V, okay, of the resistor, right? Because the resistor is the only one that causing the energy loss or power loss or dissipated from the circuit. So if you don't have the delta V across R, you may replace it with IRMS. The delta V R here is replaced with the delta V coming from the circuit, the power source, cos phi. Okay, cos phi. Okay, why is it so? Okay, if you still remember, right, the drawing, okay, isn't it? So this is delta V across R. This is delta VL minus delta VC. And here is delta V of the circuit. If you put it here RMS, so everything here also RMS. This also RMS. If you put it here max, this one also going to be max, this one also going to be max. And the angle is here, the phi. Alright, so that is how we get delta V of the R in terms of RMS value. Okay, RMS as well, yeah, because we are talking about average. Okay, so must be RMS, RMS. Right. So instead of delta VR RMS, you may also calculate it by using resolving of the phasor diagram. Alright, so delta V of the power supply cos phi, which give you delta VR RMS. Okay, so the phi here is called the power factor. It's called the power factor, okay, of the circuit. Power factor. This one is named as power factor. Right? Phase shift can be used to maximize power outputs. So remember, power factor, this one, phi is also the phase angle, right? So by shifting the phase of the current and the voltage, can maximize the power output. This is one of the method they do in the industry. Okay, so remember again, capacitor and inductor does not cause the power loss from the circuit. The only one that causing the power loss is actually resistor. And then by using power average formula IV, okay, so we're talking about average, so RMSI, RMS of delta V across R, because this is the only element that cause the loss of power. Then if you don't have this one, you may also resolve the vector, okay, the phasor diagram vector, and then figure out the delta VR RMS by resolving delta V RMS of the circuit cos phi. So cos phi here known as power factor. Alright, let's proceed. Question number 34. Right, in this question, okay, we are going to consider RLC circuit with the R of 25, L 6 millihenry, C 25 microfarad. This circuit is connected to 10 volt 600 Hz AC source. Is the sum of the voltage drop across RL and C equals to 10 volts? So madam already told you before that is not possible because of the behavior of each of the element is varied, okay, from time to time, okay, because of their different behavior. Okay, so let's prove it. So first thing first, okay, you need to calculate, okay, before you proceed with part A, you need to calculate the X reactance. XL is equivalent to 2 pi F L, which give you 2 pi times 600 times the L is 6 times 10 to the power of negative 3, which give you 20. Now for XC, it's 1 over 2 pi F C 1 over 2 pi 600, and the C is 25 micro, which give you the answer is 11 ohm. For the Z, for the impedance, it's combination of R, which is 25 square plus XL 23 minus XC, which is 11, then squared, which give you 28 ohm. Then you're going to proceed your solution, right? Then in A, right, you need to determine the sum of every delta V. Is it equals to 10 volt or not? So delta V R RMS is equivalent to, okay, delta V RMS of the circuit power source over the Z. This is representing the I, times with the R itself, okay, which give you, okay, 10 divided by 28 times with 25. which equals to 8.9. For delta V, L RMS equivalent to, okay, again we are going to do delta V from power supply over the Z to calculate the I, okay, then times with the XL, which is 10 over 28 times with the XL just now 23, give you 8.2 volts. Repeat the same step for capacitor, okay, which is going to give you 10 over 28 times with 11, which is 3.9 volt. So if you add up, okay, delta V, sum of the delta V across R, C and L in terms of RMS, you will get, okay, 20.9 volt, which is not the same to 10 volt. That's the answer, right? Okay, so part B, which is greatest, the power delivered to the resistor, to the capacitor, or to the inductor? Of course, the answer will be to the resistor only, okay, no power delivered to capacitor and inductor. Alright, and then C, find the average power delivered to the circuit. Average power, the only one that causing the loss of energy is actually resistor, right? So for C, okay, power average is equivalent to I square R, right? And then I can be calculated by using just now delta V RMS over Z, okay, and then squared times with the R. So you're going to have 10 over 28 squared times with 25. Finally, you get the answer 3.2. As we recall from our physics 1 lecture, resonance in a circuit is actually where the system giving us maximum output. So for a circuit, maximum output means that maximum current. To have maximum current, okay, we have to make sure that the Z will be minimum. Therefore, our current going to be maximum in value. This only can happen whenever the tuning frequency of the circuit reaching the natural frequency of the circuit, or F note. Okay, technically, how to do this? We only can do this whenever XL is equivalent to XC. Why is it so? Because if XL equivalent to XC, this equation going to be simplified as this. Okay, and how about this equation? This equation actually coming from this one, where, okay, XL is 2 pi F L equivalent to 1 over 2 pi F C. Okay, rearrange this equation. This F is the F note, which is here. Okay, so you will get this formula from this step. Alright, so next one, if R equivalent to 0, the current would be infinite at resonance. However, in real circuit, this does not happen. Okay, will be infinite at resonance. Okay, because even if very small, still the resistance exists within a circuit. Okay, the application of it, okay, we can tune a radio. Tuning a radio by varying capacitor changes the resonance frequency of the tuning circuit in our radio to match the station to be received. So this is the method. Changes capacitor. We use capacitor to change the resonance frequency of the circuit. Okay, to match the signal coming from the TV or radio station. So another one is metal detector. Okay, the portal is an inductor. Okay, and the frequency is set to a condition with no metal present. Whenever metal is present, it changes the effective inductance, which change the current. The change in current is detected and alarm will sound. Okay, this is on how we apply the resonance method. Number 42. Okay, the resonant frequency of a certain series RLC circuit 2.84 kilohertz, and the value of its capacitance is 6.5 microfarad. What is the value of the resonant frequency when the capacitance of the circuit is 9.8 microfarad? Okay, so as we know, the resonant frequency F0 equivalent to 1 over 2 pi square root LC. Alright, so we have 2.84 kilohertz and the value of its capacitance 6.5 microfarad. And then whenever we use a second capacitor 9.8 microfarad, what will be the frequency, right? So we need to do the ratio. Okay, so F0 natural frequency of situation 2 ratio to F0 of situation 1 is equivalent to 1 over 2 pi square root LC2, okay, over, okay, times with, okay, 2 pi square root LC1 over 1. Alright, so we can simplify this one, right? So we have L as well, isn't it? So we have finally square root C1 over C2. Okay, so if you substitute the value, right, so F natural of situation 2 is, okay, F natural of situation 1 times with C1 over C2, which give you, okay, 2.8 kilo, okay, times with square root of 6.5 micro over 9.8 micro. Finally, this is equivalent to 2.31 kilohertz. Alright. MashaAllah. Finally, this is almost the end. So if you really think about this, how come a small electron can be used to tune a frequency, to make a maximum output, okay, resonance, to have alternating current so that it can benefit our life, it can save more energy. If you are using direct current all throughout the day, the power loss will be great, so big, huge amount of power loss. Okay, so alternating current is actually important, where it can save a lot of energy, and then how to have maximum output out of our circuit. We can put it in frequency or resonant frequency so that it can tune the maximum output or maximum current that we want to have, right? So all of these can be made by using natural frequency, where we tune the electron. The electron is small and tiny things which is almost cannot be seen by our naked eyes, but then very useful in this creation of Allah Ta'ala. MashaAllah. Okay, how great Allah Ta'ala is. That's all. Thank you very much for listening and spending your time with me. Don't forget that you have this amount of tutorial to be solved. Please consult me if you have further questions.